Hi everyone, welcome to another video for research design and analysis. In today's video we're going to be talking about simple regression. And we call it simple regression not because it's super easy necessarily, but because it's just the simplest form of regression that we're going to have to deal with. Now, regression is really just an extension of what we talked about in the previous video with respect to correlations. When we were calculating correlation coefficients, we saw that we had to take the original variables x and y, transform them into z-scores, and then we could multiply those z-scores together in order to get an r value. And that r value told us about the strength and the direction of the association. But one of the disadvantages of that correlation coefficient is that it's not in the same units that we started with, right? We standardized our variables first by converting them into z-scores, and therefore we fundamentally lost information about what the actual units were on both the x variable and the y variable. So if we want to actually make informed predictions though, about like how does y relate to x, we need to actually keep those variables in their original units. So we had the example of a person's VO2 max predicting their 800-meter run time. The correlation is great for measuring the strength of that association, but if I actually want to predict a person's time, I need to do a regression instead of just doing the calculation of the correlation coefficient. So as a reminder, this is what our data looked like, right? We had a VO2 max for each person, and then we had the corresponding 800-meter time for each person. When we plotted those data, we said that there's a strong negative relationship there, right? This kind of cloud of points is tilted downward, such that a person's 800-meter run time went down as their baseline VO2 max went up. Fitter people in our sample generally tended to run faster. So what we want to do with regression now, though, is actually fit a line through this cloud of points. And it will give us an intercept and a slope that then allows us to say, given a particular VO2 max, what is the estimated run time for that person? So regression then fits this line through the cloud of points, and it will tell us in units of VO2 max what the corresponding change is in units of time. So the tricky thing though with this is how do we know what is the correct line to draw, right? Obviously I let the computer draw this white line for me, but how do I know that that's the line that best fits the data? Visually, right, clearly this green line isn't a very good fit, so we'd probably rule that out as a best fit line. Now this green line's like a slightly better fit, but you can imagine we could draw hundreds of these lines through this cloud. How do we decide which one is the best fit? Which one actually yields the best explanation of 800-meter times in terms of the baseline VO2 max? Well, the answer to that question is that we can use what's known as the ordinary least squares regression method, or the OLS regression method, for calculating the slope and for calculating the intercept. And if we know the means, the standard deviation, and the correlation coefficient, then it's relatively easy to get a calculation of the slope. Now, the reason why this is going to work, all right, and provide us the best explanation of the data will become a little more clear as time goes on. But recall that this R value, right, is related to the R squared, which is our measure of the variance explained, right? And the R value then is going to give us a slope that will give us the most variance in Y that's explained by X. So we're going to get into that in more detail in a subsequent video. But remember, in earlier videos, we talked about the mean will always give us the smallest sum of squared errors. Well, if we use this formula, we're going to get a slope that will always give us the smallest sum of squared errors. So, in the same way that the mean has the special property of giving us the smallest sum of squared errors, if we follow these formula for ordinary least squares regression, now rather than a single value that gives us the smallest sum of squares, we're going to have two values, an intercept and a slope, that will produce the smallest sum of squared errors. And again, we'll get into more detail about why that works in a subsequent video. But for now, just remember that if we use these calculations, we're going to get a slope and we're going to get an intercept that give us the smallest sum of squared errors and therefore the best explanation of the data. And just as a reminder, right, we're predicting y as a function of x. So we'll have our slope times x plus some intercept. And the slope, right, is the predicted change in y for a 1 unit change in x. and the intercept is the predicted value of y when x is 0. So hopefully you remember kind of formulas like this from an algebra class, right, at some point along the way. But again, the intercept is easy to understand as the predicted value of y when x is 0, because if x is 0, 0 times b is 0, and we're just left with the intercept. So y would be equal to the intercept when x is 0. Similarly, the slope, right, is the change in y for a 1 unit change in x, because if x goes up by 1 unit, then I would be adding b to a, and now a plus b is equal to y. If I add another unit of x, now this would be 2b, and then it would be a plus 2b is equal to y, right? So every time x goes up by 1, my predicted value of y is going to go up by the value of b. We can see that a little more clearly if we come back to our VO2 max example. So again, using those formulae, I can actually now calculate exactly what this slope should be and what this intercept should be. And most of the time, we're actually just going to let the computer do this for us, but it's important to understand what this represents and look at these formulae in a little bit more detail and do some of these calculations by hand. But the intercept here, right, is 235.68. Now, is that really a meaningful value? Not really, because that's the predicted y when x is 0, and no living person has a VO2 max of 0, right? So you can see our VO2 max data start in the 50s, because these are all pretty fit individuals, right? A lot of people might have VO2 maxes in the 30s and 40s in the normal population, but 0 would be a person who isn't breathing. They have no aerobic metabolism. So it's not actually all that meaningful, other than it provides an anchor point for this line, right? And then that's going to give us the line that best fits the data. The slope, however, is actually much more meaningful and much more useful because it's negative 1.62. So that's telling me for every 1 point increase in VO2 max, I expect your 800 meter runtime to decrease by 1.62 seconds. Right? And so that's actually very helpful for making a prediction of what a person's 800 meter runtime is based on what their baseline VO2 max was. And we can see the relationship again between this slope and the correlation coefficient, because once r is known, we can calculate b simply by multiplying by the standard deviation of y and the standard deviation of x. And this is essentially just reversing that standardization that we had in the calculation of the correlation coefficient. Because recall that r is based on z-scores of x and y. So if I multiply by the standard deviation of y over the standard deviation of x, now this is going to tell me how much change in y in the right units would I expect for a change in x back in the x units. So by multiplying by the standard deviations, I can put this back into meaningful relationships between the original units, and I get a slope and an intercept that's really useful in making specific predictions and drawing a line through my actual data. Okay, so with that equation in mind, let me give you a little bit of a brain teaser. Okay, so what would happen if we regressed the z-scores for our two variables onto each other? So, rather than regressing 800 meter times onto VO2 maxes, what if I z-transformed 800 meter times, I z-transformed VO2 max, and now I regressed those two sets of z-scores onto each other? What would the slope be equal to in that situation? Take a second to think about it, right? And then, go ahead, pause the video. When you think you have an answer, go ahead and press start again. All right, so the answer is that the slope would now be equal to the correlation coefficient, because if I've standardized my two variables, right, and converted them into z-scores always have a standard deviation of 1. So if I have my slope formula here, I'm thinking about r times the standard deviation of y and times the standard deviation of x. If I've z-transformed y, the standard deviation of y is 1. If I've z-transformed x, the standard deviation of x is 1. So I'm multiplying r by 1 over 1. So the slope would now equal the correlation coefficient, right? And again, this helps you, I hope, see the relationship between the correlation coefficient and the regression. The correlation is really the same thing as the regression. It's just done on standardized variables. But we don't always want to standardize our variables because sometimes units are meaningful. So we have to do it to get the correlation coefficient, but then we can back transform it into an actual slope in order to get something that we can use to plug in a VO2 max and get the predicted 800 meter runtime back out. Similarly, if we've standardized those variables in advance, the intercept is now always going to be 0. because the mean z-score is always 0, right? And so this is going to kind of recenter the mean at the very center of our cloud of data, because the mean of y and the mean of x are going to line up in the same place if we've standardized those scores in advance. So in practice, we probably won't really regress standardized scores onto each other all that much in this course, but this is helpful for understanding the relationship between the correlation coefficient and the regression. And as you move forward, there are likely going to be situations where you will use standardized scores, either because the units are complicated or because the units just ultimately aren't all that meaningful. So sometimes we will use those standardized scores in more sophisticated regression models. Okay, so now that we have a general handle on calculating these slopes and intercepts, keep in mind that we're doing this in order to estimate parameters, right? We're going to get a slope in the sample and an intercept in the sample. But what we're really interested in are the slope and the intercept in the population. So we want to make an inference about how these statistics map onto the parameters in the population. So much like we had a null hypothesis test for a single population mean, when we're estimating two parameters now, we're going to have hypothesis tests for both the intercept, where we'll have a null hypothesis that the true intercept is equal to 0, and the alternative would be that the true intercept is not equal to 0. And for the slope, we'll have a null hypothesis that the true slope is equal to 0, with an alternative hypothesis that the true slope is not equal to 0. And what we want to know then is, how do the values that we observe in the sample compared to 0? And what we can do is get the difference between the value that we observe and 0 and divide it by the standard error, right? Just like we did with a sample mean, we can say, was this sample mean likely to arise if the true population mean was 0? We can now say, was this slope likely to arise if the true population slope was 0? So this is very similar to what we've done with z-scores in the past. The only difference is that now we're going to be using t-scores rather than z-scores in order to calculate some kind of inferential statistic. So in order to get a t-score, right, which is always the effect size divided by the standard error, we're going to need to get a standard error for both the slope and the intercept. And here are the formulae for actually doing those calculations. Again, in practice, these things will be returned to us from a statistics program, but I want you to have these available so that you can see how those calculations are actually performed. The standard error for the slope is a little bit more complicated, but it involves taking the difference between each of the actual y values and the predicted y value and then squaring it, right? And then we divide that by n minus 2. The degrees of freedom here, right, are the number of observations minus the number of estimated parameters, and it's 2 parameters because we're estimating both an intercept and a slope, right? Then that's a little further complicated because we also have to take the variability in x into account here. So that's the sum of each x minus the average x squared, and then we take the ratio of these two terms in order to get a standard error of the slope. Once the standard error of the slope is known, the standard error of the intercept is a little bit easier to calculate because it is dependent on what the standard error of the slope is. We take the standard error of the slope and we multiply it by the square root of the sum of all the x's squared divided by the number of observations. Once we have those two standard errors, though, right, we can get a t-score for each intercept and slope. So the t observed value for the intercept, right, will be the difference between the intercept that we observe in the sample and the intercept that we assume under the null hypothesis divided by the standard error. So in reality then, right, that's going to be, or I shouldn't say in reality, but most of the time then, that's going to be what we observed in the sample minus 0, because under the null hypothesis, we assume that the true intercept is 0. And then we'll divide by the standard error, and that ratio will give us a t-score. Similarly for the slope, the t observed there is what we observed in our sample, right? Our best estimate. Remember, this little hat character means we're making an estimate. It's our best estimate of the parameter in the population minus what we're hypothesizing that parameter to be under the null hypothesis. So that's b, that's the slope we observed in the sample, minus 0, because again, our null hypothesis for the slope is that the true slope is equal to 0, and then we divide that by the standard error. So what these t-scores are telling us, right, is in units of standard error, how likely is the effect that we observed if the true effect was 0, right? How far away is it from 0 in units of standard error? And then what we can do once we have those t-scores is calculate a p-value for them to actually make a decision if we would reject the null hypothesis or fail to reject the null hypothesis in that situation. In addition to the hypothesis test, right, just like we had with sample means, we can also get a 95% confidence interval for these slopes and intercepts. And we're going to get into a little more detail about this in a subsequent video. But right, if you recall, kind of our general formula for a hypothesis test is that we can take the observed value, we can add and subtract the t critical value, right? So whatever our confidence level is, usually it's 95%, and then we'll multiply that by the standard error, and we'll go with what we observed plus the t critical value times the standard error to get an upper limit. And we'll go with what we observed minus the t critical value divided by the standard error, or times the standard error, to get a lower limit. And what that upper and lower limit will give us is a sort of two values that are compatible with the data that we observed. And you can go back and watch our previous video on confidence intervals to get a little bit of a refresher on how we want to interpret that. Right? But the idea here is that those are the two values that are still compatible with what we observed to the 95% confidence limit. Anything smaller than that, we would reject the null hypothesis because what we observed is unlikely to have arisen from anything lower than the lower limit. And anything bigger than that, we would also reject the null hypothesis because anything larger than the upper limit is also unlikely to have given rise to the data that we observed. So I know that interpretation of the confidence interval is a little bit tricky, but go back and rewatch the video on confidence intervals if you want a refresher and some visualizations on how to interpret that. But it's really the same interpretation that we would apply to the sample mean or anything else. The only difference now is that we have a unique confidence interval for the intercept and we have a unique confidence interval for the slope. But the idea would be that these confidence intervals are going to give us kind of a range of error. A and B, right, are the exact intercept and slope that we observed in our sample, but in reality, it's probably not. The true mean is probably not equal to what we observed in our sample. So the true slope also then probably is not equal to what we observed in our sample. So we want to know what a range of plausible values for the true population mean are. If we reject the null hypothesis, we know that beta doesn't equal 0. That's great, we can rule out 0. But what are some plausible values of beta? The 95% confidence interval helps us answer that question. Okay, so one final thing is I want to talk a little bit about the notation that we use in these equations. I use the symbols A and B in the linear models I presented here. So we said y is equal to b as the slope times x plus a as the intercept. Now I started with this notation because these terms might be more familiar to you from previous algebra classes. Sometimes people also write it as y equals mx plus b, where m is the slope and then b is the intercept. To avoid confusion, though, and to keep things consistent with other statistical texts you're likely to encounter, we're going to prefer a notation more like this, where we have y sub I, indicating the actual y value for a particular individual, is equal to beta 0. So beta is just a parameter in the regression model. And now if beta 0 is a constant, it's not being multiplied by anything, that is an intercept, right? That is going to be the predicted value of y when x is 0. Plus beta 1, right? So beta, again, is just a general notation for a parameter that we're estimating in the regression model. But in this case, beta 1 is being multiplied by x, so beta 1 is a slope, whereas beta 0 is an intercept. And then finally, we're going to have an error term, which is indicated by the Greek letter epsilon. And for each person's x value and each person's y value, right, we're going to get some kind of prediction here. When we plug in a value of x, we can solve the regression equation to get some kind of prediction. But that prediction probably isn't perfect. It's not going to equal y exactly. So there's going to be some amount of error left over after we make that prediction. And another way that we can write this is that we have the real data, the y, is equal to our model, which is the parameters that we're estimating times the x's, plus some amount of error. Now, moving forward, we're going to use this notation because it's really, really powerful to think about fitting your data with a model in this way, right? We have the data is equal to the model plus error. And our goal is always going to be to develop a statistical model that is a good approximation of the data. And if our model fits the data well, that means that error is going to get smaller. And if the error gets smaller by a sufficient degree, then we think that we've got a good model. Or we could even compare models in this way and say, okay, if I add a parameter here, does it explain enough error that I think it's worth including that parameter in my model? So if we're going to like this notation for everything else basically that we do as a statistical test, and you'll really see that all of the different kinds of statistical tests that we might want to do, whether it's simply comparing two groups, comparing three groups, comparing multiple factors, looking at interactions between factors, all of them are variations of this idea. Where we have some data that are being explained by a general linear model and then some error term. And our goal is always going to be to reduce that error term so that our model is a better approximation of our